Hello everyone. In this lecture we're going to talk about periodic signals. I am Touri and I am with the Electrical Engineering Department. So intuitively, periodic signals are signals that repeat themselves. So for example, in this signal, you see that a pattern is repeating itself. Or in this, that was a continuous time signal, and this discrete time signal is the same. So you see that the pattern is repeating itself. So it's an interesting thing to think about it. What is mathematical formulation for such a signal? So mathematically speaking, we say that a continuous time signal is periodic if there is a value which we call it period, and we denote it by big T or capital T. It should be positive. It's very important that it's strictly positive. And x of t plus capital T equals x of t for all little t's, okay? So for any time t, if I go forward for big T, I'll say the same pattern, okay? The smallest, and the period is not unique, right? So if it is periodic with period capital T, it is going to be periodic with period 2t, because every t it is repeating, so every 2t it's going to be repeating. The smallest such t is called fundamental period of the signal. So the fundamental period is unique, unlike the period itself. So this particular, so for the fundamental period capital T, omega naught defined by 2 pi over capital T is called the fundamental frequency because it corresponds to the fundamental period capital T. The same definition holds for discrete time signals, right? So a discrete time signal xn is called to be periodic if we have a capital N that is integer and greater than 0, so n is 1, 2, 3, 4, 5, such that capital N, such that x little n plus capital N equals xn for all integer n. So for example, capital N equals to 5. We want every 5 samples or every 5 times the signal repeat itself. So x of 1 plus 5 equals x of 1, x of 2 plus 5 equals x of 2, and so on and so forth. The same way, the smallest such an n is called the fundamental period. The period is not unique, so if n, capital N is a period, 2n is going to be period, 3n is going to be period. So the smallest such an n is called the fundamental period of the signal. And similar to the continuous time setting, we call omega naught defined by 2 pi over n naught, where n naught is the fundamental period, to be the fundamental frequency of the signal. Another terminology is that when a signal is not periodic, we call it aperiodic, okay? So for example, x of t equals to t, which is a monotone signal, is not periodic. X of n equals n is not a periodic signal, so we call them aperiodic signals. All right, so let's look at some examples. So look at this signal, which is x defined by e to the j 3 pi t over 5. So this signal is periodic, and we will see why it is periodic. So to see why it is periodic and what is the fundamental period, we need to have x of t equals x of t plus capital T for some capital T value that is greater than 0. So in other words, if we write down the definition for x of t, which is e to the j 3 pi t fifth, should be equal to the e to the j 3 pi t plus capital T over 5. And I can distribute this product over this sum, and we get j 3 pi t fifth plus j 3 pi capital T fifth. And using the product rule for exponentials is equal to this value times this value, okay? So now from the above identity, we can cancel out these values from the left and right hand side of the identity. And what we get is that we need to find a value capital T such that e to the j 3 pi t fifth equals to 1. And this holds. So e to the j theta equals to 1 if theta is a multiple of 2 pi. It's a complete multiple of 2 pi. So in other words, 3 pi capital T fifth should be a complete multiple of 2 pi, which means that t is the smallest positive number such that such a thing holds. This holds. And you can verify that the smallest such a t corresponds to k equals to 1, which gives you t equals 10/3. So the fundamental period for this signal is 10/3. So it's an interesting exercise to look at the discrete time variation of the same problem and try to find out the fundamental period of x n equals e to the j 3 pi n fifth. So we can do the same math by equating xn equals xn plus capital N, and again distributing this sum over its product and using the product rule of exponentials and using the properties of e to the j theta, we again get that this implies that j 3 pi n fifth should be a complete multiples of 2 pi. But here the important point is that n is an integer value. So we're looking for case that leads to an integer value. And the smallest integer value that we get is going to be the fundamental period. So if you vary k, the smallest k that makes this a positive integer would be k equals to 3, which corresponds to n equals to 10. So n equals to 10 is the fundamental period of the signal. So the fundamental frequency would be 2 pi over 10th for this signal. So as you can see, for the discrete time variation of this problem, we need so that the fundamental period is going to be greater than the fundamental period of the continuous time variation. A trickier question is actually this problem. So which one of these signals are periods? So it is tempting to say that if a signal in continuous time is periodic, the corresponding signal in discrete time is also periodic, and vice versa. So this is an example of such setting. So you have xt equals cosine of pi t square over 8, and xn equals cosine of pi n square over 8. And the question is that, are these periodic or not? So feel free to pause the video and think about this problem. Okay, so now if we look at the plot of these two signals, you'll see a very interesting pattern. The continuous time variation, xt, is not periodic. It doesn't look like that it is periodic. While if you look at the discrete time plot, you will see that a pattern is repeating. So it's a very curious problem. And in fact, this is true. So xt in this case is not periodic, but xn is periodic. And we will shortly see why. Okay, so why xt is not periodic? To see this, again, periodicity means that for some value capital T, we need to have x of small t plus capital T equals x of t for that period capital T. Now, what does it mean again? It means that if we write if you use the original definition, what we get is that this value should be equal to this cosine, which implies that pi t plus capital T square or 8 should be pi t square 8 plus 2k pi for some, again, integer k. what we can do is that we can cancel out all the pi's from this equation and multiply both sides of the last equation by 8 to get this equation. And in this equation, again, you can expand t plus t squared and cancel out small t squares from both sides to arrive at this equation. Now, can the left-hand side of this equation be equal to 16k? And again, k is an integer. Okay, k is some integer. So the left-hand side of this equation, as a function of small t, is a continuous function. It's actually a linear function that goes to infinity. So it swaps the whole range of real values. So it cannot stick with just integer values. So this is not true, and 2t times capital T plus t squared cannot be just integer for all the values of for all the real values of small t, regardless of what capital T is. Therefore, this signal is not periodic, or it's aperiodic. Now, let's work this out. Why xn, the discrete time variation of the same signal, is periodic? Okay, to see this, again, we use the definition. The definition is that x of n plus capital N should be x of n for some capital N, some integer value capital N that is positive. And again, you use this in the original definition, which implies that we need to have pi n plus capital N square 8 equals to pi n square 8 plus some multiple of 2 pi. Okay, so again, what we're going to do is that we're going to expand n plus n squared, multiply both sides by 8, and divide both sides by pi. And from this, we get a similar expression as the previous expression that we had for the continuous time variation of the problem. And what we get is that 2n times capital N plus n squared should be 2k times 8, which is 16k, for all integers n, for all integers n. So basically, we want to find a capital N such that 2n small n times that capital N plus n squared is a multiple of 16. And so you can verify this, that if we letting n equal the period capital N equal to 8, we will see that the left-hand side is going to be 16 n plus 64, which is actually equal to some multiple of 16. And as you can see, this is going to be periodic with period 8, and actually 8 is the fundamental period for this signal. Okay, so this is it for the periodic and periodic signals. Thank you for watching this video.